picture this. You're 5 years old and playing at a playground with your friends. All of a sudden, you start breathing quickly, your hands are shaking, and you just start to panic. Now, maybe if you're 15, 20, 25 years old, you'd be able to recognize this as a panic attack. But you're 5 years old. Your anxiety shouldn't be this bad. But for you, this is normal. Now, jump forward a few years. You're 8 years old and your parent is mad at you for not doing the dishes. They are completely screaming their heads off at you. And instead of reacting like a normal child would, crying or being sad or anything, you just sit there. You don't react at all. Again, this is not a normal response. So why is it that some children experience this? They have anxiety at a young age and then they don't react to emotions. Well, this is what I wanted to figure out using a data set. This data set looks at preschool-aged anxiety and its effect on the amygdala and the prefrontal cortex, which is responsible for mood. So the first thing we did is we took a group of 45 children who experience social anxiety or separation anxiety or just general anxiety at the age of 5, and we took fMRIs of their brains over a 5-year period. Now, an fMRI is called a functional MRI, and basically it lets us see all the connections in the brain and the way different parts of the brain are working. So the first thing we need to do is look at this data set. So obviously this data set has 45 people. And so the first thing we have is our structural data. Now there are two types of connectivity, structural and functional. In order to get the best results, we need to use both. Structural data is going to be the actual physical connections in our brain. So they're like the roadmap in your brain. You can actually see the fibers creating it. The functional data, on the other hand, is going to be the interactions with different parts of your brain. And this is especially what we're trying to obtain from the fMRI. This is really going to tell us how specific events are going to affect the way you react and why. So in order to analyze this data set, I put it into this tool called Functional Connectivity Toolbox, which lets us analyze the data we gathered from these kids in the fMRI and make sense of it. So the first step was setting it up with the structural and functional data and setting the sessions up so we have 45 participants, just like our data set. So then next we go to denoising it. So denoising a data set is basically, we just want to take our pictures from the data set, like the brain we saw before, and we want to make them clearer, more sharp, so that we can get more accurate results and just get rid of that clutter. So as you can see, we kind of center it in the middle. One of the things we do is try to find the average of each subject and take that for our data set so that we can really make sure that the entire data set is very clean and precise and not all over the place. So we eliminate anything that could be off or not really helpful for us. After we denose it, we go to analyze it. So this is going to be called the first level analysis because we are starting with each specific subject's analysis versus an overall analysis. So there are 3 different types of analysis we're going to see, and one of them is ROI to ROI, and this is going to give us a connectivity matrix. So if you don't know what a connectivity matrix is, a connectivity matrix is a graph that shows us how different parts of the brain are similar to the average. So in this one, we can see that this point, this specific part of the brain, is much more active connectively. So it's going to have a lot more connections. It's going to be more responsive to different parts of the brains, where maybe this point is going to be less responsive. And so the warmer the color, the more active the point is. The cooler the color, the less active. We can also see seed to volux analysis, and this is going to be kind of like our connectivity map, but on the brain, the specific parts of the brain. So as you can see, this subject is more of a cooler connectivity, where some of our other subjects are more warm, and this is going to give us a total idea of how the different regions interact on a whole scale. So then we can also do them at the same time, which just gives us like a combined of the matrix and the seed analysis. So after we do this and make some changes so it fits, we then go to our results, which are going to be all our combined stuff together. So the first one we're going to see is another similarity graph, another connectivity matrix, and this one is going to be more specific. It's going to tell us the exact part of the brain that is set up in the color, and it is going to also be an analysis of all the subjects combined. So that's what we're doing in the last part, was looking at each subject individually, and now we combine them for a total result. So as you can see in the cerebellum, we have a lot more connectivity than we have in the frontal gyrus or other parts. So now we're going to look at our overall results. So one of these we're going to look at is kind of like a connectivity matrix, but it's going to be in a circle form. And this way, we can look at specific parts of the brain and see all the connections it has. So this is going to be really helpful for our particular data set, because we want to see the amygdala and the prefrontal cortex and how it's connected. So the prefrontal cortex and the amygdala, they are responsible for a lot of our moods. And they actually have a lot of connections, because obviously there's a lot of factors that are going to impact our mood. So here we're going to take a look and see how that's impacted. As you can see, all the different parts are labeled around the circle here. So we're going to find the amygdala and click on it. So here is the right side of the amygdala. And so just like before, the redder the color, the more connectivity the connection has. So we can see that it has strong connections to the hippocampus, but it also has lighter connections to the prefrontal cortex areas, and not as many as we would expect to see in a healthy, normal child, which is going to let us know a signal, okay, something is off here. If we look at the left side, we're going to see similar results, just a few more blue streaks, which is pretty consistent for what we're looking for. We can also see on this a matrix in a different form. So here we can specifically find the amygdala and trace it across, and it will tell us exactly the connectivity between each part. So obviously the connectivity between the left and right lobe of the amygdala is going to be one of its highest, just because it's a similar part of the brain. And then the thalamus, we're going to see some, but then when we come over to some of the other prefrontal cortex parts, it gets lighter, which is going to tell us that something's off here. After that, we are going to look at the graph theory results, and this is just going to take a second to load. But so the graph theory results are going to be like a roadmap of the brain, but with dots. We can see all of the connections on a closer level. So, for example, we can pick specifically the hypothalamus if we wanted to look at that. Okay, so when this pops up, you're going to see a bunch of red dots. And all these red dots are specific parts of your brain and specific connection markers. So just a marker of a connection, a neural network. All the lines are going to represent these networks, and that's what creates up your brain. So I'm going to go into a selected RI, and that's basically the connection marker. So it just tells us like the specifics. And I am going to find the amygdala, and I'm going to use the hippocampus for this example because it's also responsible for a lot of mood stuff, and so I feel like this is going to give us a good thing. So as we can see here, we're seeing really limited neural networks, right? The hippocampus dots are small, and the smaller the dot, the less connected they are. So as you can see, we're still having some issues here. So what does this all mean? Basically, this just tells us that kids preschool age who have anxiety, whether it's general anxiety, social anxiety, or even separation anxiety, are going to be more prone to having reduced connectivity in the prefrontal cortex and amygdala, which is responsible for their mood. This means that they're going to be less reactive to specific situations, like a parent yelling at them. They're just going to kind of ignore the situation, and not on purpose. Something else they're more likely to experience as a result are mood disorders, which can really affect their life because they can't regulate moods the way that everybody else can. It's going to be harder for them to understand why their moods are happening and control them at a normal level. This can have a really significant impact on their lives, causing them to feel left out, or even causing them to do things like drugs or other situations they don't want to be in because they can't understand why they feel the way they do. Now, right now, there isn't a lot we can do from it. Even when we diagnose the anxiety at the age, it's often hard to treat, and just because we treat it doesn't necessarily mean we're going to see an improved connectivity. Hopefully, in the future, with connectomics, we're going to see the ability to track the specific times and places and understand why this connectivity is reduced so that we can find a specific treatment and treat them. So that kid at the playground might seem fine now, but in a few years, their lives can be totally upturned. Who knows how often this happens to kids? They're only 5, so it's hard for them to communicate. But hopefully in the future, we'll be able to understand this more.